So, just at the end of last week, we had started looking at the lattice or echo diagrams, right. So, this is a very simple circuit where you have a source voltage, a time varying voltage, which can be say a simple pulse like the mechanical pulse you saw, and has a source resistance, right, Rs, and then it is connected to a transmission line of some characteristic impedance Z0 and time delay tau 1 plus tau 2 connected to a load. For now, just let us consider simple resistive loads. So, we notice that the voltage if Rs and RL were different from Z0, we would essentially have non-zero values for gamma L and gamma S, right. And we notice that this pulse would sort of bounce back and forth till a steady state is achieved, right. So, remember that we are looking at something called the transient behavior, right. So, the voltages and currents are undergoing these changes along the transmission line for some amount of time till we reach a condition called the steady state, right. At steady state, we do not expect anything to change with time, right. So, we kind of get a certain steady state behavior, we say. This behavior, right, this speed of light delay and the bouncing back and forth is essentially to denote that there is a transient that happens from the time that the source was connected to the transmission line up to the point where we saw a steady state value for the voltages and currents on the load, right. So, I think more than drawing a diagram, right, I think it is important and customary for us to really put some numbers and do some problem solving, right. While I will try to set some assignments to help you do these kind of problems, we will also go through one during the lectures itself, right. So, I have Ts times Vs as V plus, right. So, assuming Vs is the source voltage, some fraction Ts times Vs is launched along the transmission line, and when it reaches the point C, there is some reflection, right, and this Ts gamma L times Vs would be the reflected voltage wave, right. Now, if I wanted to find out what is the voltage at C, right, just when the pulse has arrived at C, all I have to do is say that V is V plus plus V minus, right. So, I have to just simply add the forward going voltage and the reverse going voltage at any point to get what is the voltage there, right. So, this kind of exercise, rather than just working out with alphabets, let us try to take a simple problem with numerical values and try to go through this, okay. So, here I have given some numbers, right. So, let us start with this. I have a voltage that is being generated, right. You can also think of this as just a 12-volt battery and a switch, right, and I am just closing the switch at time t equals 0, right, and I want to understand the transient behavior, right. So, one thing that circuit theory has already taught you is how to estimate the steady state behavior, right. So, if for a long time t after the switch has been closed or after t equals 0, if I just asked you what is the voltage, right. So, we will be looking at voltages at 2 points. So, we will call this say V in and this V out, right. So, if I asked you what is V out and V in at steady state, circuit theory just tells us that the transmission line is a short circuit, right. So, V in is V out in the long term, right, and you can simply use a resistive divider rule, right. You can say that the current flowing at steady state, so I am going to call ISS, SS standing for steady state, is simply 12 volts divided by the total resistance, right, which turns out to be 12 volts by 300 ohms, right, is equal to 40 milliamps. Okay. And if I asked you what is V in or V out, both are the same, and you would say that this is simply from the Ohm's law, I steady state multiplied by the load resistance RL, right. Here RL is 200 ohms and RS is 100 ohms, right. So, you can just say that this is 40 milliamps times 200 ohms. This would give you 8 volts, right. You may even have heard of some simple formulas, right, saying that it is RL by RL plus RS times the voltage, right, for resistive dividers. Nonetheless, right, even with that you should get 8 volts, right. So, we eventually expect that V in and V out settle down at 8 volts, right. Now, the real question, right, that transmission line behavior helps us analyze is what happens to V in and V out on its way to 8 volts, right. So, circuit theory would have told us that this 8 volts is established instantaneously, regardless of how long the transmission line you use to connect between the 200 ohms and the 100 ohm source resistance, right. But transmission line theory is saying that no, this is not going to happen instantaneously, even though you turned on the voltage from 0 volts to 12 volts instantaneously. The steady state value is not going to be established instantaneously, right. So, there is going to be a speed of light delay, there is going to be multiple bounces of the voltages and currents if the characteristic impedance is not the same as RL or RS, right. And in that case, there will be a significant delay between the time that you turned on the generator to go from 0 to 12 volts and the time that you measure 8 volts at the input or the output of the transmission line, right. So, this is what we called transient behavior, right. So, we are going to now derive what the transient behavior, transient voltages V in and V out look like for this particular case, right. So, we have to start with the echo diagram. So, I am going to plot time as an axis going down, and then we have the length along the transmission line as the direction x, right, and we will call this the input, right. So, we have V in, or let us call this point A, and this as point B. Okay. So, first thing is when we turn on this 12 volts, how much of that 12 volts actually gets launched as a forward propagating wave on the transmission line. So, we have to essentially first find out our transmission and reflection coefficients gamma L and gamma S at the source. So, let us start with that. So, we said the Ts was simply Z naught by Z naught plus Rs. In this case, we can evaluate this to be 50 by 50 plus 100, which is 1/3, right. So, I just want to make a comment here. It's very interesting, right, that this Ts, right, which is the transmission coefficient, only seems to be dependent on Z naught and Rs, right, and it doesn't seem to be dependent on RL, right. So, some way to kind of verbalize this in English is to say that the transmission and reflection coefficients are only dependent on local impedances, right. So, since RL, right, the information that there is RL connected at the end of the transmission line is not known to the fields, right, near point A, right. So, whatever happens at A is determined by only the local impedances, which is only the characteristic impedance of the transmission line and the source resistance, right. As you may say, the system is not yet aware that there is a load of 200 ohms, right, connected to the other end of the transmission line. When am I saying this? This is just after time t equals 0, right. So, t equals 0 plus, you can say that the system is not yet aware that there is a load resistance of 200 ohms at the end of the transmission line, right. Similarly, gamma L is RL minus Z naught by RL plus Z naught, which is 200 minus 50 by 200 plus 50. This is 3/5, right. Similarly, gamma S would be 100 minus 50 by 100 plus 50, which is 1/3 again, right. So, gamma S and Ts seem to be the same. Okay. So, now we have Ts, gamma L and gamma S. We can actually draw the bounce diagrams, right. So, we have one-third of 12 volts, which is 4 volts, right, traveling in the forward direction. And when will it reach point B? For the first time, the delay of the transmission line is mentioned as 1 microsecond. So, we will say that this is at 1 microsecond, we have reached from point A to point B. Okay. So, let us make our divisions 2 micro, 3 micro, 4 micro, right. So, we will just do a few of these bounces just to give you a sense of how exactly the voltage, right, at say V out or V in can be estimated as a function of time. So, I am going to have okay. So, since this is a step, right, a function step from 0 to 12 volts, right. So, you can sort of think of this as a wave front, right. So, the source is holding at 12 volts, right, for all times after t equals 0, right. So, now we have 4 volts as my forward propagating voltage, right. So, it is slowly charging the entire transmission line, and think of all the little capacitors, distributed capacitors that we saw, right. They are all charging up to hold 4 volts across the plates, right. And you can also consider some amount of current. We will do the same analysis for currents, right, in the next, where we will talk about the inductors also getting charged, right. So, we have a 4 volt being sent across the transmission line, right. This is coming up from saying that V plus is Ts times Vs, right. So, I am going to say that 12 volts is Vs, Ts is 1/3. So, 1/3 of 12 volts is propagating and charging up the entire transmission line for over 1 microsecond, right. And then what gets reflected? So, I have to have V minus going in the backward direction is given by gamma L Ts times Vs, right. So, what can we say this is? So, gamma L is 3 by 5, Ts is 1 by 3, so 1/5, right. So, 1/5 of Vs. So, that is about 2.4 volts is being reflected back, right. So, now if I were to ask you what is the voltage at B when this arrives, when this 4 volt arrives, is going to be, so V at B at time t equals 1 microsecond is always V plus V minus, right. So, remember that gamma L is positive, right. So, V minus is plus 2.4 volts, right. So, V plus was 4 volts, V minus is 2.4 volts. So, the net voltage seen would be 6.4 volts, right. So, if I were to plot V out as a function of time at about 1 microsecond, I will see a jump to 6.4 volts. Okay. So, V out was 0 volts, right. Even though at t equals 0, I turned on the generator, V out will continue to remain to be at 0 volts till about 1 microsecond, which is the speed of light delay through the transmission line. And when the 4 volt V plus arrives at B, there is a reflection because the characteristic impedance is not the same as the load impedance, right. So, in some sense the system is understanding that the load is not matched to the characteristic impedance. So, some portion of the signal is being sent back, right, almost like a messenger carrying information, right, about the source and the load back and forth. You are sort of having this transient behavior, right. All right. So, now this 2.4 volts. So, for the time 1 microsecond to 3 microsecond, I expect this 6.4 volts to be constant, right. So, V out stays at 6.4 volts for a duration of 2 microseconds, right. Why is this? Because the reflected voltage has to come back to the source and then come back again to the output, right. So, it is 1 microsecond each way. So, each time V out or V in gets updated, right, with a new voltage, there will be a gap of 2 microseconds, right. So, it is the to and fro delay of the transmission line, right. Similarly, if we were to plot V in as a function of time. Remember, V in is at the source location, right? So, as soon as the generator turned on to 12 volts, the V in will immediately see the impact of that, right? But remember that not all of the 12 volts shows up at V in, right? So, it is Ts times Vs, right? So, we only see 4 volts. So, this is 1 micro and then we have 2 micro. So, till about 2 microseconds, we have a voltage of 4 volts showing up at the input terminal of the transmission line, right. So, this is a step in understanding. So, V in has 4 volts, whereas V out goes to 6.4 volts, and there is a time delay. There is a lag between what the V out voltage is and the V in voltage is, right. So, we are allowing for different points on the transmission line to have different voltages at different times, right. All right. So, now this V minus is going to reach the input point A, and there is going to be a reflection gamma S, which we said is 1/3, right. So, there is a new V plus that is going forward now, right. Which is essentially gamma S, gamma L, Vs, sorry, Ts, Vs. Right. So, gamma S is 1/3. So, when I do 1/3 of 2.4 volts, I get 0.8 volts, right. So, this is 0.8 volts. Okay. So, now if I were to say what is the voltage update, right, at point A at 2 microseconds, that is the signal has gone once to the end and come back. What can I say? It is simply V plus plus V minus always, right. So, in order to evaluate what is happening here, we have V, right. So, remember that we have V plus from the first launch, right. So, that is Ts Vs plus gamma L Ts Vs plus gamma S gamma L Ts Vs, right. So, the sum of all the voltages, the entire history, right, because remember the input voltage is not a pulse, right. If it was a pulse, the situation would be different. In the case of a step, remember that the source voltage is 12 volts for all times, right, and remember we have to approach the 8 volts at steady state, right. So, it is approaching this 8 volts in very small steps, right, and the steps are diminishing in height, right. So, here we would have 4 volts plus 2.4 plus 0.8. Okay, this turns out to be 7.2 volts. Okay, so at 2 microseconds, I'll have a step up to 4 microseconds. I have a small increment in voltage, right. So, you can see that we are slowly approaching 8 volts, but we are sort of doing that asymptotically, right. So, you can think of this way, the very first time the voltage along the transmission line gets charged to 4 volts, right. So, the entire transmission line, the central conductor and the outer conductor gets charged to 4 volts. Then when it reaches the 200 ohm load, there is a 2.4 volt reflection and it is of the same sign. So, that 2.4 volts now adds on to the original 4 volts, right. So, now the entire line gets charged up to 6.4 volts, right. So, when I am coming backward, the currents and voltages are essentially charging the line to 6.4 volts along the entire transmission line. Then again there is a reflection at the input, right, and the reflection is an amount 0.8 volts. Now, this 0.8 adds on to 6.4 to give us 7.2 volts and the entire line gets charged to 7.2 volts, right, and then there is a reflection again, and then we are going to see that the line is going to eventually get charged up to the steady state value of 8 volts uniformly throughout the entire transmission line, right. This is what you expect, right. So, remember that say you had a battery and then you took a pair of long wires, right, and then just connected it, the leads of the two wires, you take it and connect it to the battery. You expect the voltage of the battery to be showing up at the end of the two leads as well, right. So, if I were to take say the 9 volt battery and then I have some very long cable and I connected this cable to this battery, I expect to measure 9 volts at the end of this, right. But we are saying that this does not happen instantaneously, right, that it will probably have a transient behavior. The moment you make the connection to the point when I actually observe 9 volts will not be at the same instant of time, right, that there will be a certain delay of this 9 volts showing up at the output, right. But nevertheless, after all these multiple bounces that is happening, you do expect the output to be at 9 volts, right. So, similarly here the generator has turned on and switched on to 12 volts and the steady state voltages at both the input and output of the transmission line is 8 volts, but we are just saying that it happens through various transitions, right. All right. So, I think this is perhaps sufficient. I would recommend that you can probably continue this in process, right, and you can try to understand this. Perhaps some examples through your assignments also can help you continue to get some better and clearer understanding in how to solve this, right. So, I can at least tell you that we expect both V in and V out to eventually reach the steady state value of 8 volts, right, but it will do so in some sort of a asymptotic fashion, right. Okay. So, hope you can go through this as many times as you want in order to understand what actually is going on within the circuit. Okay. Now, we will look at the current side of things.